All right. Hi, loves. So, I apologize if you hear any sirens or like cars outside. My windows are all open, and Finn is about to come over and freak out because I'm recording a video and talking. And so, if you hear anything in the background, those are the floofs. So I apologize ahead of time. Okay, so today we're going to talk about 7.1 and 7.2. The book talks about exponential growth and decay together. So I just put them, like they put it separately, but we should just talk about it together because they're very similar. So this is how I do the notes. I also have it all filled out. So you can pause and take the notes down and then listen to what I have to say. Or you can kind of listen to the video and then go back and take it. Whatever floats your boat. I do not care how you take these notes. Okay, so the exponential function for growth and decay is going to be y equals b to the x power. And so let's talk about growth first. Exponential growth is going to be if the b is greater than 1, it is growth. And so your domain is always going to be all real numbers, and then your range is going to be from 0 to infinity. And now that may change once we do the transformations, but for like the parent function, it's 0 to infinity, and then you have an asymptote at y equals 0. Now, when you go to graph this, you are always going to have your x values be negative 1, 0, and 1, and then your y values will always just be 1 over b, 1, and then b, and then you can graph that function that way. Okay, now if we have b, so again, going back to this function y equals bx, if b is in between 0 and 1, it is going to be this exponential decay. Your domain is going to be negative infinity to infinity, and your range is going to be 0 to infinity with that asymptote still at y equals 0. You're still going to have your x values be negative 1, 0, and 1, and then your y value will be 1 over b, 1, and then b. Okay, so that's just the kind of generic function of exponential growth and decay. When we're talking about transformations, we are going to go back to the Hackett method. Okay, so you're still going to start with, you're always going to start with the negative 1, 0, 1, and then 1 over b, 1, and then b. And then you're going to just do the Hackett method, which is what we've been doing since September, October, right? So our Hackett method is when we have the function, instead of y equals b to the x power, we now have an a out front, we have an x minus h, and then we have the plus k. Okay, all of the transformations are still the same that we have been doing since last semester. If a is less than 0, it's a reflection. If it's in between 0 and 1, it's a shrink. If it's greater than 1, it's a stretch. If it is if h is greater than 0, it's right h units. If it's less than 0, it's left h units. And then this is the important piece because your k tells you your horizontal asymptote. Oh, sorry, both dogs are over here, so they're about to go crazy. Okay, calm down. So let's just kind of talk about this, and then we'll go from there. Okay, so remember your equation is y equals a b x minus h plus k. So in this case, you will always have an a. It won't be 0. So a in front of the 3 is just the 1, b is 3, h is negative 1, and k is 0. So I always define my variables, or my not variables, but my letters, and then I always find my asymptote and plot that right away. I also determine whether it's growth or decay because that will tell me whether it's going like this for growth or if it's going down like that for decay. So with the growth, if you look here, I have the negative 1, 0, 1, and then 1 over b, 1 and b. And then my h, remember, you just hack it. So h goes on the left, so you're going to minus 1. And then once you do that, you can cross that out. And then this becomes, remember, your ordered pair. So negative 2, comma 1/3, negative 1, comma 1, 0, comma 3. You plot those points, you connect them. So after you plot those points, you know it's growth. So it'll be approaching the asymptote, and then it'll go up like that. Your domain, like I said, is always negative infinity to infinity. Your range is 0 to infinity because this is always your h value right there. Okay, let's talk about B. So this is still growth because the letter that's touching, or the number that's touching x is greater than 1. My A is 1/2, my B is 5, like I said, so it's growth. My H is 0, and my K is negative 2. So remember, your K tells you your horizontal asymptote, so I plot that right away. And then again, you do your negative 1, 0, 1, and then your 1 over B, your 1, and then your B values, and then you just hack it, and you go from there, and then you plot your points. So again, I did those points, and then I connected the dots. Now notice Finny, come here. Your domain is still negative infinity to infinity, and then your range is negative 2 to infinity. Sorry, guys, that he was barking. Okay, let's talk about some decay. We also have a reflection going on. So, this is, again, start with defining your A, your H, your K, and your B. So remember, y equals A, B to the x minus H plus K. If you need to write that out to get going in the beginning, that's okay. So A is negative 1, so that tells me there's going to be a reflection. So instead of going like this, it reflects over and it goes like that. My B is 1/6, so it's decay. My H is 0, and then my K is also 0. So I have an asymptote at 0. Now, because it flips it over, your domain is still negative infinity to infinity, but your range is now, instead of going from here up for your range, remember you always read range from bottom to top. So you start at negative infinity, you go up to that 0. Notice that you also have parens because it's an asymptote, so you don't want brackets. You want your parens. Okay. With this one, this is also decay because your B is 6/10 or 0.6. Your A is still 1 because that's in front of your B value. Your H, you always change H and keep K. Your H is 3. Your K is positive 4. So that means you're going to have an asymptote at y equals 4. And then again, you just start with your generic negative 1, 0, 1, your 1 over B, your B, and then your B. Okay, so in this case, you have 1 over 6 over 10. And then in order to get rid of that, stop, he is moving closer to the camera to annoy me. And then you multiply by the reciprocal. I'm so sorry that they're squeaking twice. Okay. So, and then you just plot your points, and then it's decay. Honestly, these are one of my favorite graphs to graph because they're very straightforward. Domain is negative infinity to infinity. Your range is 4 to infinity. Okay. Everyone's favorite is word problems. So 2 that we are going to work with in this section is y equals a 1 plus or minus r to the t power, where y is your final amount, a is your initial amount that's given, r is representing your rate of growth or decay as a decimal. That is very important, as a decimal, not the percent, and t represents your time. So that is general growth or decay problems. Now, if we're talking about interest, right, a lot of growth and decay that we're going to see in the real world, and this is why I love this chapter, is because it's talking about like how it's compounded yearly, or like how, like it's like talking about money or like depreciation of a house or a car. So in this case, if we're talking about interest n times per year, we use the function a equals p times 1 plus r over n to the nt power, where a represents the final amount, p is the initial amount, r is the annual amount as a decimal, and then n represents the number of times compounded per year. So like how many times it's happening per year. So like quarterly would be 4 times. And then t represents the number of years. Okay, so a couple of things I want color coded. So example 2 is the purple and example 3 is the blue. So you deposit $500 into an account that earns 2.6 annual interest. How much will you have in your account after 4 years? So semi-annually. So literally I just define everything. So P is 500, R is 0.026, T is 4, and then twice a year because it's semi-annually, so N is 2. And then you just plug everything into your calculator. Make sure you use parentheses. So your end amount is $554.43. So if I were to ask how much you made, you could say that you just made $554.43. Sorry, Finn is okay. I hope it's at least making you laugh on this blizzard day. Okay, a cup of green tea contains approximately 35 milligrams of caffeine. Finn, come here. Come here, Finny. Okay. The average teen can eliminate approximately 12.5% of caffeine from their system per hour. Use your graphing calculator to find out how much remains after 4 hours. So you could just graph this equation right here, where it's you start with 35 milligrams, you're decreasing at 1 minus 0.125 because that's how much you're losing it. And then to the x power. So you have to plug in x when you graph it. And then if you wanted to find out how many, like if you want to do it by hand, you could just plug in 4. Or in order to find the 10% milligrams, you could just go over to, you can plug in the y. 10% of that would be 3.5, right? So you can trace it over and you can find it that way too. Okay, of course, now that my video is almost done, they're quiet. I hope this brought you some entertainment either tonight or on your blizzard day. But please complete the notes and then the homework assignment. If you have any questions, please email me. We'll touch base. I'll start class with this on Thursday. Tomorrow's Wednesday. So go ahead and take these notes. I hope you all have a wonderful evening or afternoon. I'll see all of your lovely faces on Thursday. Okay, bye, loves.